Okay, so today we're going to start talking about design, software design. We've talked about a number of issues that relate to design earlier on in the course. All the stuff in Chapter 5, for example, was relevant to design, the class material. The material in Chapter 6 on patterns, especially as we moved forward into the more design-oriented patterns, that's also relevant to design. And so is the material in Chapter 7 and 8. The user interface side is part of design. And so is the material on dynamic and behavior aspects and UML notation part of design. But what we're going to see today are different aspects of design. We're going to take a look at the principles and then later on the architecture. Okay? So today we're going to talk about design principles, and this will wrap together a lot of the important concepts and help you to understand what's a good design, what's not a good design. So first of all, let's say what design is. Okay, we can define it as a process. Okay, sometimes the final document is also called the design, but we're going to primarily consider design a process. It's a process to implement the functional requirements within the constraints of the non-functional requirements. And the non-functional requirements set the boundaries. They say, in some sense, well, you have to have at least this efficiency, and you have to have at least this response time, and this maintainability, and those kinds of issues, while you are developing some kind of computational mechanism that will make those functional requirements be adhered to. Okay, and all the while you're going to have to adhere to general properties of good design quality. You know, these properties of design quality we'll talk about, such as testability and cohesion and coupling and so on, will also help you to achieve the functional requirements. But they're not normally written in the functional requirements. The functional requirements and they're not written in the non-functional requirements either. The requirements are written to solve a particular problem, and it's sort of taken as a given that you're going to do good design as you're doing that, as you're developing those requirements. Okay, so the design process then involves a series of design issues that we have to resolve. Now you've seen this concept. When you are doing your requirements, in the current assignment, you're writing down issues that you have to consider in requirements. Well, it's the same thing in design. When you're doing design, you have a bunch of issues. Do I do this approach, or do I do that approach? And you make a decision, okay, from several options. Okay, so this concept of design decision, which commits you to a certain path in your eventual implementation, is key to design. You make a series of design decisions, and eventually you end up with a complete design. And the idea is that you choose the best option from among the alternatives, but best is often somewhat subjective, depending on your background, depending on very fine balancing of a number of forces that play upon the decision. You know, one designer might make one alternative choice and another might make another. Okay? So for example, one of the most common design decisions is, do I do this in, say, Java or C++? Well, you know, if you're a Java programmer and you know a lot about Java, you'll be biased towards Java. If you're a C++ person and you really know you can create reliable C++ code because you're good at it, and it takes somebody with more skill to do good C++ code because it's very bug prone, well, you might be biased because you might say, well, I can do good code here, and furthermore, I think that I can achieve an equal level of reliability, but greater efficiency, perhaps. And so that might be, you know, your balancing decision. But somebody else might say, look, you know, I'm going to use Java because the people who are going to be maintaining this know Java better. It's less bug prone, and efficiency is not that important, okay, for this particular application. Okay, so they're making design decision, one or the other. And ideally, each decision has an optimal, but it often doesn't. Okay, so in order to make a decision, you have to have knowledge. Knowledge enables you to make decisions. You need knowledge of the requirements, of course. Okay, you need knowledge of what design decisions have already been made, because they will force you to make certain subsequent decisions. If you've chosen Java, well, then you have chosen a path that will lead you to choose, say, do I use Swing or AWT or something else, you're not going to be, you know, if you've chosen Java, choosing to use the Microsoft Foundation toolkit for C++ as your class library, right? That doesn't lead in that path. Another piece of knowledge is the technology available. You need to understand your technology, understand your computing technology, understand your software library and framework technology, any hardware device technology, etc. You need to understand design principles, which is today's topic, and best practices. You'll notice that throughout this course I've been saying, and that is a software engineering best practice. Okay? Well, this is an engineering concept of a generally accepted way to do something that should be used. So, for example, doing use case analysis is now, and most people in software engineering consider it an engineering best practice to at least give a list of the main use cases, even if you don't do them all. And also a knowledge, and this comes from experience only, of what worked well in the past. Okay? A lot of engineering is just based on one's experiences and the experiences that have come from others. A lot of this is encoded in design patterns. Okay, we said that they are a way of encoding experience in what constitutes good design. There's the concept of design space. Okay, design space, we can imagine it as a graph with nodes and arcs, and each of the nodes represents a state of the design, and eventually we're going to reach, if we can in fact lay it out as a tree, although it's more like a lattice, if we lay it out as a tree, as we move from, say, in this diagram from left to right, we're making decisions and committing ourselves. And the number of possible nodes that we can reach subsequently gets narrowed down. Because, for example, if we make the decision to go client-server, then we've eliminated the monolithic option and all of the decisions we could have made from that point. If we then go to thin client, we've eliminated fat client and all the possible design alternatives that would lead off from that. If we make the decision to go to separate user interfaces layer from the client layer, or a separate user interface layer for the client layer, then we've eliminated another set of design decisions. And so the space, the initial space, is all the possible designs we could do, and as we make decisions, we narrow it down and reduce the number of possibilities. But often this design space is very, very large, okay? And you have to get a perception of all the possible designs you could do, all the possible variations, and knowing those variations allows you to analytically decide, based on pros and cons, which alternative to choose. Some terminology now. Component. Okay, component is a word that you hear a lot in today's software engineering discussions. I have defined it as any piece of software or hardware with a clear role. Okay? Some people have a slightly different definition. Maybe it's something which can be unplugged and plugged in somewhere else. I wouldn't necessarily go to that level of detail, but basically, you know about hardware components, transistors, ICs, circuit boards, things like that. Software components have a similar role in software. They're pieces of the design that can be separately designed and typically plugged into a design. Typically, they can be used in multiple designs. Okay, but although that isn't necessarily the case. One of the key things about components is that you can say whether or not it's reusable or not. I can take this component out and I can replace it with another component which perhaps has a better design at a later date and time. Okay? So the concept of component is that you can replace it, and it's easy to replace. Okay? You can't just take any old file in a program with say, Java code and replace it easily, because you have to understand how other files take advantage of it, other classes use it. But if it's a component, then it's got a well-defined interface so that you understand what you need to do to replace it with another equivalently functioning component. So in hardware, a motherboard might be a component, and I know the interface to that, and I can replace it with another motherboard that has better functionality. But it will still have the same interface, and will therefore still work in the same design. Many, although not all. Many components are designed to be reusable. Okay, so reusability of components is one of the objectives, often. And the very fact that you've got a well-defined interface helps to make them reusable. But they're not always reusable. Sometimes they're very specific to a particular need, and therefore there will be no need for them anywhere else. Okay? Another piece of terminology that we often hear, the word module. Again, this has been used over the years in many subtly different ways, although the general broad concept of module is well understood. Okay, and I'm calling a module a component defined at the programming language level. So it's a component, but it's a type of component that is defined by a programming language. So a class, a method, etc. is what I'm considering a component. There are other components that are not defined at the programming language level that you might define as part of your design, that put together as groups of classes or sets of packages, sets of files, all of the code that exists on one particular computer that runs together, things like that can be considered components too. An executable module can be a component. Okay. But if it's defined at the programming language level, such as classes, methods, and packages, okay, then I'm calling that a module. Okay, and so this notion of module, by the way, was invented not right at the beginning of the dawn of computer programming in the 50s. It came slightly later than that, when people began to realize that they couldn't just put their code into one big mess and expect it to work. They had to modularize. They had to organize things into logical groups, and then the programming languages started supporting this modularization. And that was the dawn of modularity. So we had languages coming along, such as Pascal, that had strong modularity. And that's why I'm defining it as a component at the programming language level. The notion of system is also something that we often talk about. So what is a system? Well, there's a whole area of science called system science. Okay, in fact, there's a system science graduate program here at the University of Ottawa, and in many universities there are systems engineering programs. A system is a logical entity having defined responsibilities, okay, as I'm defining it, or objectives, and consisting of hardware, software, or both. In fact, we can broaden that description to say it's any kind of entity that we can discuss that has responsibilities or objectives. So we can talk about a biological system. You as a human being are a system, okay, whose objective, well, we won't talk about what your objectives are, okay? You have personal objectives, and then there are biological objectives in your genes, etc., etc. There are ecological systems that are broader in the whole ecology. Typically, the ecology's, it doesn't have an intelligent objective, but it wants to survive, it wants to thrive, it wants to reproduce, etc. There are certainly complicated systems that involve many different engineering artifacts. This building can be considered a system that has subsystems, which are also systems, consisting of heating and lighting and electrical and plumbing and so on. Okay. So a system has a specification. In the software context, we can write a specification for a system. We should have a specification, ideally, the requirements, okay, of what this system is going to do, and it's implemented by a collection of components. So what distinguishes a system from a component, or what, in particular, a subsystem? We said we can break systems down into subsystems, right? It says that at the bottom of the slide. A subsystem is a system that just happens to be part of a larger system. The way I distinguish is that the system is the thing that has the specifications. And even if I take all the components out and replace them by all different ones, still the same system. Okay? Still the same logical entity that's fulfilling the same requirements. So the components are those things that build the system and make it implement those requirements. The system as a whole is a logical level entity that has a specification and is made to work by the components that compose it. Okay? Okay, this is my perspective. You can read the way I've written this up in the book. Took quite a lot of going backwards and forwards between me and some books reviewers to hone this thing down. But I think that this is a generally accepted definition that helps people to understand what a system is. The whole notion that you can replace components is very important. Okay, it's still the same system. In fact, you can imagine an electronic device where components wear out over time and you keep replacing them. So eventually, none of the components are the same components, but same system. They talk about, in biology, many of our cells get replaced as life goes on. You know, in particular, our blood cells get totally replaced. You've got totally different blood cells today than you had some years ago. But, you know, still you, and your blood system's still the same blood system, right? Okay? So that's the notion of system. It's something that survives the entities that compose it. I've described these concepts of systems, subsystems, and components as a UML diagram. Okay? So I'm saying, well, we have systems which have subsystems, and by the way, our subsystems are systems. Okay? So I'm using a generalization and an aggregation here. Okay? So we see something that looks like the general hierarchy or composite pattern, which indeed it is. And that means that we can have a whole hierarchy of systems and subsystems. And I'm seeing that systems in general, whether they be full systems or subsystems, are implemented using components, one or more. And components have subcomponents. So I'm using a reflexive association to model that hierarchy. Okay, and one type of component is a module that's defined at the programming language level. Another type of component is a framework. Yes, a framework is a component. Okay? Any questions up to this point? Yes?
You said components are replaceable.
Ah, and what about frameworks?
Yeah.
Ha, I knew somebody was going to ask that. It might be harder to replace a framework, but you could do it. For example, you could say, well, we've got this version of OCSF, and somebody's come up with an improved version of OCSF that has all kinds of different internal mechanisms inside it. And as long as it presents the same interface to the code, to the implementations of the hooks and the slots, you can replace the framework. It's just got to have the same interface, right? Might have different ways of mechanism internally for doing its work.
The hooks and slots.
The hooks and slots have to stay the same. They're part of the interface. Yeah. If it's a true component, they'll stay the same. Or you know, there should be compatibility so that you might add some new ones. You know, and you might make some. You might declare that some are deprecated and so on. Slightly weaker notion of component then, but still, you could replace that component. Very good question. Now that shows that you're on the ball on this. Yes?
So let's say that OCSF is a component of a system. What would be the greater system?
Well, the greater system would be the implementation of your, for example, simple chat. But don't forget, you can also have a system which is implemented as one component. You know, it's a degenerate case, but you can imagine that you have a small program that is implemented using one module. Still a system implemented with a component in some sense. I mean, I say a component, and you can replace that. You can replace that module. You can reprogram it. You can say it's the same system. You know, from the perspective of the end user, they don't need to know that it's changed. Right? That's a bit of a degenerate case. The more obvious case is the way you're replacing smaller components of a larger assembly. Design strategies, top-down versus bottom-up. Okay, top-down design is where you first of all start with the high-level structure of the system. What is the main program or the main class? And maybe you start with a high-level framework and then you build details on from there. You work down making decisions about the classes and then the methods, and eventually you get to the low-level details of particular data items and arguments and variables and algorithms at the bottom level. Okay? But you start off with an overall diagram of the architecture and work down strictly from top to bottom. Bottom-up design says that you start by creating utilities that you're going to be able to reuse. And then you put them together into higher level utilities. and you work from the bottom until eventually you just have to glue together a few reusable components and bang, your system exists. Okay. In practice, neither top-down nor bottom-up design is used very much. Top-down design is used more than bottom-up design because ultimately bottom-up design tends to be harder to really make everything reusable and pluggable in from the bottom without even thinking about the top. It's pretty hard. There are some circumstances, for example, if you're doing programming where your reusable components are Unix, typical Unix programs, and you're writing scripts to put them together to do things. That's a form of bottom-up design, and I've often sort of written reusable little C programs that will filter data and things like that, and then I plug them together. Sort of bottom-up design. But in reality, you still have some kind of an idea of where you're heading towards, and you still have got a rough top-down concept somewhere, even though you might be doing the details bottom-up. So in reality, most design is a mixed approach, okay, or should probably be a mixed approach, even if it actually isn't. You need to have the architecture concept and to think of how you're going to break the system down into subsystems and sub-subsystems and the components that are implementing them. At the same time, you also need to think about what are the opportunities for reuse and do some bottom-up design where you're building reusable components from the bottom, because then you'll end up with designs that are more flexible. The reusable components give you that flexibility, and they give you the reuse itself. You know, you can reuse them later on in other projects. We talked about that extensively in earlier chapters. There's other types of design. Software architecture, some people even consider that a whole separate field from software engineering, or at least a major area that warrants, you know, a separate treatment from software design. And we can talk about software architecture or architectural design as the division of the software into its components. How do we make this division? What are the criteria for making these divisions? What kind of components, and how are they going to interact? Class design is the design of classes and the methods. We talked about a lot of those issues in Chapter 5. You typically don't design one class, you design a related set of classes that's working together in a package. It's often still called class design. User interface design, that was the subject, or key subject of Chapter 7. Some people move it out of this area of design in this chapter and consider it separately, and I've done that, in fact, in this book. I've considered user interface design. It has enough distinct features that it warranted its own major section of a major chapter, just like class design did. Algorithm design is also another area of design that is often moved out. In fact, we're not even talking about it in this course. I'll briefly talk about a few algorithm design issues in the testing chapter, because you have to understand algorithms to do testing effectively. But in reality, you need to take a course in algorithm design, and a lot of the sort of CS1, CS2 data structure material involves some algorithm issues, so you will have learnt algorithm material already. And it warrants a software engineer to take advanced courses in algorithm design as well. Certainly our software engineering students do that, and it's quite important. Protocol design is then the design of the messaging that is sent over networks, typically, or generally speaking over networks. And that has its own science and whole branch of software engineering that we've alluded to. We've talked a little bit about some issues of protocols earlier on in the course, but it's another area you can study. So all of these areas on this slide 12 then are areas of software design that can warrant their own study, and there's a lot there to be learnt, and each can have its own course, effectively. In fact, the last four, class design doesn't have its own course, but user interface design, algorithm design, protocol design do have their own courses at the University of Ottawa. Software architecture is the main topic of another third-year software engineering course as well. So let's talk about the principles that underlie many of these aspects of design. The principles are aimed towards achieving certain quality goals. These quality goals are things that we talked about in Chapter 1 and we've revisited from time to time. Usability, efficiency, reliability, maintainability, reusability, and others. Others that are not mentioned here because they might be more important in specific circumstances. Safety is certainly one that's quite often important, especially in real-time systems. Okay, and design might be that might be a primary issue in design that we really have to worry about. But it's not always. Sometimes, if we're just doing some numerical calculations, safety is not a concern. I mean, the hardware might blow up, but the software is not going to have any effect on that. Other goals are increasing our profit or reducing our cost. We want to make designs that are cost-effective and have the best economic effect for us as an organization. That's often achieved by having the best economic effect on our customers, because then they will buy our product or buy more of our product. We want to conform to the requirements. This will indirectly affect the profit we make. Accelerating development will also directly affect the profit we make. If we can get the system developed faster, costs us less money to develop and maybe makes more money for the customers as well. Okay? So these are some of the goals, and it's important to have an understanding of what our goals are. Many of these goals are the same goals we had when we were doing requirements. But when we get down to design, it's important to rethink our goals and to realize that some of the goals, especially these quality goals, are things which may not be explicitly talked about in the requirements. First design principle, divide and conquer. This principle is a universal engineering principle. In fact, many of these are universal engineering principles. Okay, this applies whether you're doing electrical engineering, computer engineering, chemical engineering, mechanical engineering, even many aspects of civil engineering. Okay? You don't just say, I'm going to design this entire complex system in one fell swoop by one person. I'm going to break up the design and deal with issues one at a time, because anything else is too complex for the human being to deal with. I've got to break the problem up so that a human being can grasp a particular subproblem, solve that subproblem, and then contribute that solution to the solution of the larger problem. Divide and conquer is one of the things that human beings developed in the early days of antiquity. Okay, we learnt that you can have organizations, you can have governments where different people are responsible for governing different things. Okay, military people learnt that rather than try and attack with one army in massive clashes, that if they try and break up the opponent's army into several sub-armies, that they might have better success. Okay, so dividing the enemy and conquering is easier than attacking the enemy all at once. So we have separate people on each part of the system. It allows specialization, so now you can specialize in those parts that you have been assigned. Each individual component is smaller and less complex, and you can replace the parts. Okay, if you do a Big Bang design, a design of the whole thing as a whole, well, there's no piece that you can identify to replace if you discover you did a bad design. But if you've divided the thing up into components, and one of those components is bad, you can replace it. Okay? So that's a universal issue in all of engineering, the ability to break things up for many, many good reasons. And keep that forefront. I put this first for a reason. It's one of those principles that is needed for all the other principles. Okay, we're going to talk about coupling and cohesion. But unless you've divided up the system, you can't even think about the notions of coupling and cohesion. You can't think about the notion of reusability. It is one of the primary, if not the primary, engineering design principle. Okay? And doing it, it's not just dividing and conquering, it's doing it well. It's effective dividing up. That's the key. So you can divide up a software into subsystems that are clients and servers. Okay? Even if you don't actually need to operate over a network, just dividing a system into client and servers that are going to operate on the same computer can help to separate concerns in a strong way that you get this good replaceability. You can replace the server, you can replace the client. It forces you to define effective protocols for communication. You can't bypass those those communication channels between client and server. Okay? You've got to communicate over that channel and got to define the protocol. Okay? If you just divide things up into classes and packages, you can cheat by having code access classes that you didn't expect it to. But if you've got separate executables that communicate, that's a very strong division. It might sacrifice efficiency. Okay? So you have to trade off. All these things in software engineering are trade-offs. And efficiency is one of those things that sometimes says, don't divide, keep together, because otherwise we have an efficiency cost of dealing with the division. But generally speaking, dividing is good. You can divide a system into subsystems, broadly speaking. You can divide a subsystem into packages, which are also subsystems. You can divide a package into classes. You can divide a class into methods. So these are just finer and finer grained levels of modules or subsystems. Okay? Your choice of how you do it. Okay? Generally speaking, you're going to do all of these things. Each of the subsystems should have its own well-defined interface, its own design. People can understand its design, see how it interacts with the other components. Questions? Principle 2, increase cohesion. What is cohesion? Well, I say that something has high cohesion if it keeps together those things that are related to each other and keeps other stuff out. Okay? Keeps together things that are related and keeps other stuff out. So cohesion is a measure of the organization of your system. You've broken things up and you've put the right things in one place and the wrong things in another place. Or things to do with networking in one place and the things to do with user interface in another place. Or the things to do with floating point numbers in one place and the things to do with integers in another place. Okay? Rather than mixing them together. Okay, so you can modularize and divide up, but have a bit of the I.O. here and a bit of the I.O. there, and a bit of the database here and a bit of the database there. You're still divided and conquered in some sense. But it's much better division if you have high cohesion. You look at a module, subsystem, and you can say, I know exactly what this does. It does this category of stuff. And that category of stuff is only done here and not done somewhere else. And that's one of the things you want to aim towards in good design. There are a number of types of cohesion that are well identified in the literature. We'll talk about some of these in a couple of minutes. There can be very strongly cohesive modules or subsystems, which we say can be functionally cohesive. And there's layer cohesion, communicational cohesion. We'll talk about what each of these means in a minute. Utility cohesion is basically a kind of cohesion that says these are modules which are reusable, but we can't identify where else they go. So we're going to put them together in this one place. Because they're utilities. That's the only thing that binds them together. Okay? So let's talk about the types of cohesion. Functional cohesion. Functional cohesion is considered the strongest form of cohesion. The concept is that if something's functionally cohesive, if you provide input and it gives you a single output, and that's all it does. Okay, so a function mathematically is functionally cohesive. A mathematical function takes some input, transforms it, and produces an output. Okay, it doesn't do anything else other than that. It doesn't have side effects, so it isn't, oh, by the way, modifying some other variable that isn't part of this function. In fact, a true mathematical function doesn't modify any variables. It just computes something and returns a result. And that's the concept here. If you have a functionally cohesive module, it doesn't save any results. It doesn't change any variables. It just takes input and gives an output, and then it's up to you to choose what to do with that output. Okay? And that functionally cohesive module shouldn't do anything else other than that. It should only do that one thing. Okay? Now, you can program a method as functionally cohesive. So a method that simply takes an input and gives you an output. Doesn't save the results. in an instance variable or any kind of variable would be functionally cohesive. You can also have a whole subsystem as functionally cohesive. You might have a subsystem whose job is to filter some sound from in some kind of streaming sound source. Okay, so imagine that I'm inputting sound using some standard sound encoding, and I'm filtering out certain frequencies, and then I'm outputting the sound in the end. Okay, inside that subsystem there might be a lot of stuff going on, a lot of methods, a lot of data manipulation. But ultimately, if the only way that you can interact with this system is to put sound in and get a modified sound out, and it always works the same way. Put the same sound in, I get the same sound out. Therefore, it's not saving any temporary information internally or externally. It's just inputting and outputting, and it always works the same way. It's functionally cohesive. Okay? It would not be functionally cohesive if it was to save temporary variables, save its state, cache data, so it might behave a little bit differently next time. That would break the functional cohesion. It isn't necessarily bad to break functional cohesion. We're just identifying functional cohesion as the strongest form, and it's desirable. It doesn't mean that you always have to achieve functional cohesion. It's just a good idea to think about whether you can, if you know, as an alternative. It gives rise to designs that are highly flexible, that you can easily replace components because you just have to understand the input format and the output format, and you can replace it. There's no fiddly stuff going on where you have to save results and things like that internally. Okay, benefits: easier to understand the system, more reusable, easier to replace, and as I said, modules that update a database or create a file, interact with the user. By definition, these things are not functionally cohesive because they are having effects that are other than just inputting some data and spitting out an output. Yeah?
So some code that, for example, in audio plugins that, amplifies.
Okay, code that amplifies in audio plugins, right?
So is that cohesive or?
Functionally cohesive.
Yeah, functionally.
Talking about functionally cohesive. Well, as long as that's all it does. If it only does that, and it isn't saving its state so that next time it might behave differently, for example. If it did that, it wouldn't be functionally cohesive. It might still be very cohesive. It might still be a good design, but it wouldn't be functionally cohesive. Okay? Any other questions? So functionally cohesive is the end of the spectrum. It's the most cohesive kind of thing you can do. Layer cohesion is another very desirable form of cohesion. This is a form of cohesion where we say that all the facilities for providing or accessing a set of services are kept together and everything is kept out. One of the key words here is services. Okay? A layer is providing a set of services to a system. And generally speaking, layers form a hierarchy. You have higher layers and lower layers. In telecommunication systems, we talk strongly about layers, layered architectures. You'll learn about that in more advanced courses. But there's the notion of the transport layer. Below that, you've got the data link layer and the physical layer. The physical layer is the hardware. Okay? Transport layer is the layer for sending packets over the network. And above that, you have the application layer at the top, which is the email application mechanism. Okay? And so you might have, at each of these layers, you might have APIs. Okay? So the API is, as we've said before, is the public facilities that can be accessed of any module. A layer is one of those things that has APIs. In fact, any well-designed module will have an API. A key concept about layer cohesion is that higher level layers can access the service of lower layers, but, and this is key, lower layers do not access higher layers. Okay? If lower layers access higher layers, you've broken the layer cohesion. So slide 19 shows some examples. On the left, a standard kind of diagram that shows some layer cohesive modules. Let's start from the bottom, because the bottom modules are the ones that are providing services to the higher ones. operating system access. You have a module whose job is to provide operating system services of some kind. Maybe reading, writing files, opening terminals, sending messages over the network, things like that. Okay? That's all it does. It's cohesive because it does that and doesn't do anything else. Remember, that's the definition of cohesion. It does a set of things and excludes others. Database access is providing a set of database access services. That's all it does. It doesn't do other stuff. It doesn't do UI, doesn't do operating system stuff for you. It just does database stuff. And network communication. Okay? All it does is provide a set of services that allow you to communicate over the network. Now, these things are probably not, in fact, most likely not, functionally cohesive because they're going to be storing data. If I save some data to a database and then I try to save the same data again, I'm going to get different results. I'm going to get a message saying you've already saved it. Okay? So it's not functionally cohesive because if it was functionally cohesive, it would always have the same results each time I did the same thing. Whereas in this case, it's going to have different things. Operating system access is the same. If I create a file, the next time I try to create the same file, the same command, it's going to have different results. It's going to come back with a message saying file's already there. Okay, so it cannot be functionally cohesive. But it can be layer cohesive. Layer cohesive means that it's providing a set of services upwards to callers. Okay? Application logic then might be another layer cohesive mechanism. It calls services below and provides services above, but you don't see any arrows violating this downward direction of access. Okay, if you saw those kinds of arrows going the other way, then you've broken the layer cohesion. Any questions? Here's another example. This is an example in an operating system internally where we have calls from a higher level layer cohesive module to a lower one, as before, but we can also show that you can bypass. You can call the immediate lower level layer, but it's also possible in some ways of designing layers to bypass and call layers further down. As long as you don't have upward pointing arrows, still layer cohesive. It's a slightly weaker form perhaps, but there is still layer cohesion there. So for example, the application program might well access directly some kernel facilities that are very low level, to do with locking processes and things like that. Changing the priority of processes. That's possible. It certainly might call screen display facilities to display its output on the screen. And these themselves might call some kernel process mechanisms. The screen display facilities might call user account management, which might call the file system module. File system module calls the kernel, but the user account manager also calls the kernel. Okay? So, still layer cohesion here. Calls going down, modules that typically have side effects, that store results, and aren't functionally cohesive, but there's still strong cohesion here. It's layer cohesion. Each of these modules, we can identify what it does. It does just this stuff and nothing else. So the file system stuff just does file system stuff and nothing else. The user account management does user account management and something else. It's going to use the file system stuff to do it, but if we ask what does it do, it does it does user account management only. That's all it does. If it mixed other stuff, if it did a bit of screen management too, we would say that breaks the cohesion. Question?
Can you give an example how the screen display facilities would use the user account management?
It might very well be that depending on your permissions, okay, you aren't allowed to display on the screen. It might be that the screen display facilities, part of it is the logging on screen, which has to access the user account management for that purpose. Okay. Yes?
You say that if the user account management uses screen display facilities, that it breaks cohesion, right?
In this, yes. Okay. Now, so this might not be an ideal operating system design. I'm using this as an example of layers, and what you're saying is that, well, what if What if we needed to have the user account management stuff display the screen facilities? Remember, we're not talking, this is an operating system internally here. The application programs sit at the top. And so the application, one of the application programs might be logon application, which would call screen display facilities, and which would one of the screen display primitives might be, display login or something like that. This might not be an optimal design from that respect. But if you wanted to design it with layer cohesion, make the calls go down and not up. And you might have to juggle your layers to get that to work properly. It might be that we shouldn't have screen display facilities calling user account management. We should have two parallel layers with a third layer on top that calls both of them. Maybe that would be a better design. So one of the sets of design decisions that you're going to be making here is how are we going to orient these layers so that we only have calls going down the chain and not up the other way. And finally, on the right-hand side, we have this notion of communication protocols. They're often considered to be 7 layers, but I'm just showing you a few very simple issues here. Dealing with application protocols, we'll call the facilities for dealing with connections, which we'll call the facilities for dealing with packets, which we'll call the facilities for transmitting and receiving. But the calls don't go up the other way, if it's true layer cohesion. Communicational cohesion. Again, anytime you see a type of cohesion, you say, what is it that belongs together and what else are we keeping out? In communicational cohesion, it is the manipulation of data. All of those things that manipulate a certain kind of data are kept together, and everything else is kept out. Okay, so stuff that deals with a different kind of data is kept out. So the ultimate in communicational cohesion then is the class. Ideally, a class is a module which is there to manage a particular kind of data. And that's the only place where that data is managed. The instance variables are private, and it provides an API, a set of messages that other classes can use to manipulate that data. So that's the ultimate in communicational cohesion. But there are other forms of communicational cohesion. You could have a database module that manages just one kind of data, or you could have a server that is maintaining a particular kind of data on the server end, and all it does is manage that kind of data. Okay, maybe it's data that has to do with login and user access information, and you access that module. Okay, if that's all that module did, manage that data, you would say it's communicationally cohesive. Now, it might well be, by the way, that a communicationally cohesive module is also layer cohesive, in the sense that it provides services and you only have the links, calls to it. You don't have calls from it to things that call it. That would also be layer cohesive. And hey, there might even be communicationally cohesive modules that also are functionally cohesive. It's harder to imagine those circumstances, but I could probably cook some concept up. So when you're doing object-oriented design, you're thinking communicational cohesion. A lot of the stuff I've taught you about good design of classes is going to help you achieve communicational cohesion. If you stick stuff together that doesn't belong together in a class, you're breaking communicational cohesion. Okay? Now we're going to move down into types of cohesion that are still cohesive, but are weaker. We can talk about them, and sometimes you have modules that have this kind of cohesion and lack the others. That might be okay. Sometimes design trade-offs lead you to have weaker cohesion for very good reasons. But generally speaking, you're going to try to achieve communicational cohesion and/or layer cohesion and/or functional cohesion. Sequential cohesion says that if you have a bunch of procedures where one is calling another, and that is calling another, okay? And further beyond that, one is providing data to the next, and the next one is providing data to the next. So they're passing each other data in a sequence. It's desirable to group these together into some larger module, rather than have these things in totally separate parts of the system. Okay, it would be rather bad if this part of the system does the first stage, passes data to a totally different part of the system, does the second stage, passes data to a totally different part of the system to do the third stage. Occasionally that might be needed, but it would be a good design quite often to group those things together and say, well, we're going to do those 3 steps of the pipeline in some higher level module and keep them together. And if you do that, it's called achieving sequential cohesion. It's putting things together where data is passed around from step to step, grouping them together in a higher level. Now, the individual things, the individual procedures, might very well be functionally cohesive. Or there might be layer and communicational cohesion in the internal pieces. But grouping them together in some higher level component or subsystem is where you want to perhaps achieve sequential cohesion. Okay? And then procedural cohesion is one step away from that. Procedural cohesion is saying, well, we're not passing data around, we're just doing step 1, step 2, step 3. It's very similar, except that the data is not flowing from step 1 to step 2, and data is not flowing from step 2 to step 3. They're just 3 steps. And if you group them together in one place, you're achieving what's called procedural cohesion. Okay? And it's procedurally cohesive, as with all cohesions, if it only does those things and doesn't do other stuff. Okay? If it does other stuff too, you don't have the cohesion. It's got to just do these things that are logically step 1, step 2, step 3, step 4, step 5. And if there's other stuff that is done by some other use case or something else that's bunged in the same place, you've broken the cohesion. So you should be able to look at a procedurally cohesive module and say, I know what that does. That does these 5 steps of the process. It doesn't do anything else. It just does that. So classical procedurally cohesive steps are initialization sequences. I've got to initialize the database. I've got to initialize the network. I've got to initialize the user interface. Step 1, step 2, step 3, somewhat independent of each other. Certainly not functionally cohesive because they have side effects that last as the program executes. Not really layer cohesive because they're doing a bunch of stuff that traverses a whole bunch of layers. Maybe there's layer cohesion there too. But the key of why you group these things is because you're doing a bunch of stuff that's done step 1, step 2, step 3. And actually that leads us to a special case of procedural cohesion, which is if the operations are done at one point in time during execution and then typically never done again, we call it temporally cohesive. Temporal means time-wise, okay, relating to time. Okay, so temporal cohesion is that you have some pieces of the execution that are done at one point in time, typically initialization or termination of the system, and are not used anywhere else, not used at any other time, then we say there's temporal cohesion. Okay, it might be a function which is executed at tax time once a year, and you're grouping all of those functions together that take data out of your database, prepare a tax return, and that's it. And you might say, okay, well, what's the logical reason for doing the grouping? Okay, whenever you think of cohesion, you think, what's the logical reason? The logical reason for grouping in that case is because these are the stuff that is used at that period of time. Okay? What's the logical reason for grouping in communicational cohesion? It's the data access. By the way, that word communicational cohesion is confusing because it sounds as though it's to do with sending messages. You just have to learn that. It's called that for historical reasons. But temporal cohesion is easy to understand because the word temporal in English means relating to time. So things that are done at a point in time or period in time, and that's the reason for grouping them together. It may be weaker than procedural cohesion. I said it's a special case. You can certainly have procedurally cohesive things like initialization steps that are temporally cohesive. But you can also have things which are done together but aren't necessarily step 1, step 2, step 3, like stuff that has to do with end-of-year financial arrangements that isn't necessarily step 1, step 2, step 3, but is done at that point in time. And you can group them in a module. One of the general guidelines in choosing a cohesion to use is to think we want to aim towards stronger cohesion. If you have a decision to make, do I go with weaker cohesion, do I go with stronger cohesion, you generally speaking want to go with stronger cohesion. So you generally speaking want to go with layer cohesion or functional cohesion or communicational cohesion rather than temporal cohesion. Unless you just got a bunch of stuff and you want to group it in some way, and there's no other way to group it. And you say, okay, well, rather than randomly scatter them around, we'll group them together by the time they execute. Temporal cohesion. So it's a way of grouping, it's a weaker way of grouping things when you've got no stronger way of doing it. Okay? And finally, utility cohesion. This is the kind of cohesion you get when you say, I got a whole bunch of stuff left over now. What do I do with it? Well, if some of those things are reusable code, then put it in a module that says, this is the place where we keep our reusable stuff. It might be a package of reusable code, or a subsystem that's got a bunch of packages in it. Okay? It's better to have the utilities in one place than scattered around so people can't find them. And so that's why I have this term utility cohesion. This is, by the way, my invention. That you don't see this in most other books. But the other ones are standard. You see them in all the other books. Okay? Any questions then about these notions of cohesion? Yeah?
The math class can also be considered functional cohesion?
Okay, his question was about math. Okay, if we have a class in Java called Java, .math, the individual methods in that may be functionally cohesive. Right? An individual method that computes sine or cosine or something like that is presumably functionally cohesive. But the class itself, what kind of cohesion do you think the class itself has? It would seem to be utility cohesion because it's grouping together utilities. It's grouping together related utilities, so it's not just any old utility. So it's quite a good, strong utility cohesion. But it's fundamentally these are methods that can be called any old place. Individually, they're functionally cohesive. As a group, the group has utility cohesion. So we can consider the cohesion at any level. The lowest level method, what's its cohesion? Okay. Methods can be functionally cohesive. Generally speaking, classes can't be, because to be functionally cohesive, you just have to have one calling point. Right? If I have multiple methods on the API, by definition, I'm not functionally cohesive because I have more than one thing that I'm doing. I have to be doing just one thing. So if a class has just one public method, it might well be functionally cohesive. As long as it's not saving any instance variables during the course of executing. So that next time its variables affect the calculations the next time that method is called. Okay? One of the typical exam questions is I give you a description of a type of system and I say, what kinds of cohesion is here? What kind of coupling is here? Okay? So that's the kind of level you have to understand. You'll become much better at these concepts of cohesion and coupling when you take more advanced courses and you get practice doing much more significant designs. Right now, you should learn the concept and begin to recognize when you see different kinds of cohesion. And now we'll talk about principle 3, which is coupling. Coupling is the jewel of cohesion in many respects. We want high cohesion, we want low coupling. Generally speaking, as you push towards higher cohesion, it'll help you to get lower coupling, although they are somewhat independent. And I've done some studies. One of the areas of research I do is exactly into cohesion and coupling and how to achieve it in designs. I have some graduate students working on this. And we did some experiments a few years ago. The general wisdom was that as you increase cohesion, you decrease coupling. But we discovered some circumstances where it didn't work that way, where you can increase both and or decrease both at the same time. But generally speaking, as the design gets better, cohesion goes up, coupling goes down. Coupling is interdependency between modules. Interdependency between components in general. Okay? We want to reduce interdependency because the more interdependencies we have, the less flexible our system is. Interdependency means that a change in one place will force us to change something else. Because if this is the one place and this is the other place, okay, if I make a change in this and add something to it that makes it behave differently, okay, then this one is going to have to change to reflect this change. It's going to have to say, well, now I'm going to have to behave differently in response to this change. All right? So interdependencies need to be reduced in order to have a system that's easier to understand and a system where you can replace the components more easily. Ideally, you've got almost no interdependencies, no dependencies of any kind. I use the word interdependencies because you think in both directions. Okay? Dependency is typically a one-directional thing. Interdependency is typically two-directional. You have to think both ways. But ultimately, an interdependency is just two dependencies. The big network where everything's dependent on everything else is really, really difficult to understand and change. Some types of coupling we'll look at in a few minutes include content coupling, inclusion coupling, external coupling, etc. We'll look at all of these. But the diagram at the bottom of slide 25 illustrates some points. Thick lines mean stronger dependencies, and thin lines mean weaker dependencies. And the number of lines is also important. So on the left, I've got a lot of dependencies and a lot of big, thick ones. So for example, the two rightmost boxes, the two rightmost modules on the left diagram have 3 arrows pointing down. That's 3 somewhat weak dependencies. Towards the center, I've got some thicker dependencies that I'm showing. On the right, I've got an improved design where the number of dependencies, or the amount of coupling, has been reduced. Okay? So now I only have thin lines, and fewer modules are connected, and no place do I have multiple connections between the same 2 modules. So the number of connections and the strength of the connections is important. Both are important together. Number and strength. And you've got to reduce the number and the strength. One of the design patterns we talked about has a big impact on reducing the dependency among classes. Okay, can anybody remember the pattern that we talked about that has that impact on reducing dependency among classes? Come on, somebody can get this. Reducing dependency among classes. Nobody can get that. Okay, you're going to have to really study that. Yeah, okay.
Delegation.
Delegation. Right. If we don't do delegation, we're going to be having all kinds of classes connected to all kinds of other classes. With delegation, we can reduce the number of linkages because we can cut it down so that there's only one place where classes are hooked together rather than many places. And classes are only hooked to their neighbors rather than a network of connections. Okay, so if you only connect to your neighbors, you're going to end up with many fewer connections than if you connect to all of your other classes, and furthermore, all the parts of you connect to all the other classes. So the total number of connections need to be reduced, and the strength of those connections need to be reduced. The strength has to do with the amount of data passed over the connection, or the frequency with which that connection is used as execution goes on. The fragility of the connection in terms of the sophistication of the methods, the messages that are passed, the difficulty of understanding those connections. Those things have to do with strength. Okay? So reduce the strength and reduce the number of connections. You get lower coupling. And lower coupling is one of the key software engineering principles. Let's take a look at some kinds of it. Content coupling. Content coupling is arguably, or no, without doubt, the worst kind of coupling. Content coupling is where one component modifies data in another component, and the other component can't stop it, and worst of all, that isn't even aware that its data is being modified. Classic examples occur when you have instance variables that are not private. If you have public instance variables, then any other Java code anywhere in the system that gets a hold of one of the objects can start fiddling with its data. Okay? And the code that controls that class has no way of knowing that this is happening. can't intercept those calls and log them. It can't prevent them. It can't raise exceptions when they occur. If you have public instance variables, opening yourself up to the world. Okay? One of the things we definitely see is that we have modules in operating systems that have no content coupling, and force you to use APIs to access them, because if you could fiddle directly with the operating system, you can crash your computer in no time at all. Okay. If you can fiddle with data in another executing program, you can crash the computer, or you can violate security by accessing things you shouldn't be able to access. And so we need strong boundaries to minimize the amount of ability to get inside the data space of modules. Okay. So as a general rule, we should completely avoid any kind of content coupling. Okay. There were days in the early days of programming when there was an even more insidious kind of coupling, where you could actually modify the code of a running program. It's like going into Java and modifying the bytecode as the program is running. Okay. If you did that is just awful, awful, awful design. Okay. Sometimes the content coupling can be a bit insidious. These two classes here illustrate an interesting case. Let's take a look at them. We've got a class called line, okay, which has a start and end point. And it's got public methods get start and get end. Straightforward enough. We've got a class called arch. Okay, so an arch, maybe looks like this. Okay, composed of a set of lines. It has a baseline, okay, that says what kind of base it's sitting on. I mean, this is a very artificial example, but it's to illustrate a case. Okay, that baseline has a slant. Okay, that slant is an integer value of some kind. Maybe it's the angle in degrees, and we can change the slant. This thing here says we can get the end of the baseline, and then we set the location of the end. Okay, and what's going on here? If we look at this last line, it says the end. Okay, the end is the end point of this line. Okay, we're saying set location. So we're setting the location of the end, and to do that, we're getting the x, okay, and we're replacing it with a new y. So we're saying get the x value of this point, and that's going to be the location of one end, and the new value is going to be the y point. The key point is that even if data is private, if you have access to the variable, you can still make changes internally. If you have a method that gives you the variable, you can still internally change the data, sometimes surreptitiously. Okay? Common coupling. Common coupling is the use of global variables. Okay? Global variables in the early days were the only kind of variables. All variables were global. And then people came up with the idea of having local variables in functions and procedures. Okay, that was a good idea. And then people realized, well, that's the only way you should do it. You should only have local variables. And then people came up with instance variables. And that's good too. Okay, because that's encapsulating objects. Fine. Global variables are bad because anybody can change them anywhere, and all the people that can change them, all the methods that can change them, don't know who else has been also able to change it. Okay? So you have coupling effectively from this global variable to all of the parts of the system that access or could access that global variable. So it gives you a strong and diffuse kind of coupling throughout the entire system. If we can get rid of global variables, we can and encapsulate the global variable in a piece of code where you call a method, then that method has control over that data and can block access and can keep track of access, and you can change the design, and you can find out all the calls that take place and so on. And you end up with a better design. So the general rule of thumb is get rid of all global variables. And static variables, public static variables, are a kind of global variable. They're a bit weaker, but they are a kind of global variable because they have the same effect. Instead of saying declare X as global and now anybody can modify and access X, all I do is I put X inside as a static public variable inside class Y, and I can just say y.x, and I can change y.x anywhere, and I can access y.x anywhere. Okay? So public static variables are effectively global variables, and that's one of the reasons why we don't use them. You also want to avoid public static methods too, but public static variables are a lot worse. So global access, where everybody can access something, is bad. It's still a kind of coupling that's not global coupling, it's not common coupling, when you have a subset of the system's classes, like a Java package, can access everything. Okay, so if you have a variable, not a public static variable, but just an ordinary static variable inside a package, okay, it's not global because the outside the package can't access it, but it still is accessible to everything in that package, and so you should still encapsulate that. It's not quite so much common coupling, but it still is similar. There's only one or two exceptions. Global variables are useful sometimes for debugging. You have a value which you access for the debugging process, and then you get rid of it later on. I've done that. It's reasonable. As long as you have only one or two of them, it's probably okay. Sometimes in certain kinds of systems for system-wide default values, if the thing is a constant, it's better. Only changeable in one place. Okay? You can imagine using the read-only interface pattern to achieve that in some sense. Something like that. And the singleton pattern is the pattern that we use to encapsulate global access to an object. Okay, so I have my airline class with the airline object. Okay, I have get airline. So there is, in some sense, a global object there. There's one object that's accessible from everywhere, but I'm accessing it using the singleton pattern as an instance variable of that singleton class using a method. All right? Control coupling has to do with connections among procedures, or methods, or functions. And it occurs when one function has strong control over what another function does. Okay, rather than just calling it with some data and saying, please give me a result, it is passing flags that say, do this, or do that, or do that, or do that. And there's a switch statement, or if then else, big if then else block inside the caller, sorry, the callee, the thing that's called, that says, well, if my caller tells me to do this, I'm going to do this. Otherwise, I'm going to do this. Otherwise, I'm going to do that. Okay? So if you have this strong kind of calling, it's called control coupling, where one module tells another module exactly what to do. In some sense, we have control coupling in the simple chat system, where messages come in over the network, and we have this handle message from client that basically says, if the message is this, I'll do that. If the message is that, I'll do that. If the message is that, I'll do that. That's a kind of control coupling. How do you deal with that? How do you weaken control coupling? Well, one strategy is to use polymorphism. One strategy is to have a handler which basically says, depending on the name of the message, I'm going to call a function with that name. Okay? Rather than doing each of the actions myself, I'm just going to, whatever the caller says, I'm just going to call a function with that name. So I'm not going to actually execute different things inside me. I'm just going to call a different function with a different name. And polymorphism gives you that by saying, okay, well, if I'm a circle, I'll behave this way. If I'm a square, I'll do area calculation this way, and so on. So getting rid of switch statements. Signs of switch statements, anytime you see a switch statement or a big, long if then else that's predicated on a value, it might well be, and it probably is in many cases, control coupling. And it just shows a strength of connection between two modules that should be reduced if possible. You can use a lookup table. You can use polymorphism. There's a number of ways of reducing the strength of these connections. Okay, the lookup table takes this strong connection and puts it into a separate place, and so that people can flexibly modify the data as opposed to having the two modules tightly connected. The data is what controls the interaction as opposed to the tight connection of the modules. Okay, so here we have if command is this, then do that, else do that. That's control coupling. If instead we had polymorphism controlling what is done, then we have got rid of the control coupling. Stamp coupling is when I pass data structures around. Okay? Anytime I'm making a call to a procedure, there is coupling going on. Okay? We want to reduce the strength of that coupling. Okay? And if we pass complicated data structures, that is a stronger connection than if we pass simple data. Sometimes you have to pass complicated data structures, but it's better and weaker coupling if you can pass simple data, integers, floating point values, strings. Okay? So think about seeing if you can weaken the coupling by removing the stamp coupling, which is your strong coupling. And so here I have an example where, I know the time, here I have an example where I am passing an employee and a string, send email employee string, and instead I can change that and simply pass name, email address, and text. So I'm not passing the entire employee. The thing that's doing the sending of the email doesn't need the employee object. So why pass that entire object? Why not just pass the name of the person and the email address of the person that I got from the employee object? I'm weakening my coupling. I'm increasing the number of arguments, which does increase coupling a little bit, but I'm weakening coupling overall because stamp coupling of passing an entire object, I don't need to have the employee class coupled to my emailer class. Okay, every class knows about strings, and so that's fine. Passing strings is totally innocuous, but passing an employee class to the emailer class couples together the entire employee class, the email class, because the emailer class can't be used unless it knows about the employee class. Okay, so that is stamp coupling, and you can avoid it in a number of ways. We'll pick up the other types of coupling in the next lecture. Okay.